Welcome. In this video, we are going to solve MCQs of AP TRANSCO 2019 exam. This exam consists of two parts, Part A and Part B. Part A is of 70 marks, 70 questions, which is related to electrical questions. And Part B is 30 questions, 30 marks, which is related to general awareness. Question number 1. A high Q quartz crystal exhibits series resonance at omega s and parallel resonance at omega p. To answer this question, we need to know the structure of high Q quartz crystal, which is like this. In a high Q quartz crystal, series resonance omega s occurs when motional inductance Lm and motional capacitance Cm resonance, and parallel resonance frequency omega p occurs when Lm, that is motional inductance, Cm motional capacitance, and shunt capacitance Cs resonates. Since there is additional capacitance in parallel resonance frequency is greater than series resonance frequency, but shunt capacitance in a high Q quartz crystal is very small. Therefore, the gap between omega s and omega p will be very small. Therefore, we can say that option D is correct. The present output Qn of an edge-triggered JK flip-flop is logic 0. If J is equal to 1, we need to find the future output, that is next state output Qn plus 1. The next output Qn plus 1 of an edge-triggered JK flip-flop can be written as J into Qn bar plus K bar into Qn. It is given that Qn is equal to 0 and J is equal to 1. Substituting this in the formula, we get Qn plus 1 is equal to 1 into 0 bar plus K bar into Qn, which is equal to 1 into 0 bar is 1 plus 0 into anything is 0, and therefore Qn plus 1 is equal to 1. Therefore, option D, logic 1 is correct. Question number 3. The minimum number of 2:1 multiplexers required to realize an 8:1 multiplexer is. By using the generalized standard formula, n:1 multiplexers required to make m:1 multiplexer is m-1 by n-1. Here we need 8:1 multiplexer using 2:1 multiplexer. Therefore, substituting in the formula, we get 8 minus 1 by 2 minus 1, which is equal to 7. If you don't remember the formula, this can be answered by simply taking 8 inputs and converting into one output by using 2:1 multiplexers. This can be done like this. Take 8 inputs, that is 0, 1, 2 and so on until 7. Use only 2:1 multiplexers and try to get the 8:1 multiplexers. This can be done like this. The number of 2:1 multiplexers used here are 1, 2, 3, 4, 5, 6 and 7. Therefore, the total number of 2:1 multiplexers required to realize an 8:1 multiplexer is 7. Option C is correct. Question number 4. The contents of resistor B and accumulator A of an 8085 microprocessor are 4, 9 and 3A in hexadecimal form respectively. We need to determine the contents of A, status of carry flag and sign flag after execution sub B instruction. In an 8085 microprocessor, the sub B instruction means A is equal to A minus B. Here A is accumulator. To perform the subtraction here, let us use 2's complement method. To perform subtraction using 2's complement method, we need to convert 49 hexadecimal and 3A hexadecimal to binary values. 49 in hexadecimal form can be converted to binary format using zeros and ones as 0, 1, 0, 0, 1, 0, 0, 1 in binary format. Similarly, 3A in binary form can be written as 0, 0, 1, 1, 1, 0, 1, 0. The value of 49 in hexadecimal in decimal format is 73. And similarly, 3A in hexadecimal converted to decimal value gives 58. In microprocessor, subtraction is performed using 2's complement method. For A is equal to A minus B, A is equal to A plus 2's complement of B taking complement of each binary value and then add 1, which is 0 1 0 0 1 0 0 1 complement plus 1, which is equal to 1 0 1 1 0 1 1 0 plus 1, which is equal to 2's complement of B is 1 0 1 1 0 1 1 1 in binary value. Now let us perform sub B instruction, which is equal to A is equal to A minus B. The value of A is 3A in hexadecimal, which is equal to 0 0 1 1 1 0 1 0 in binary. We need to add 2's complement to the value of A to get A minus B, that is 2's complement of B is equal to 1 0 1 1 0 1 1 1. Adding this gives 1 0 1. After executing sub B instruction, the value in accumulator A is this, which is in binary format. Let us convert this into hexadecimal, which is F1 in hexadecimal. We have used borrow to do this calculation. Since borrow is required to do this calculation, the carry flag value CY is equal to 1. And the most significant bit MSB is 1, which indicates that the value is negative. Therefore, sign flag S is equal to 1, which can also be verified by using A minus B, that is 58 minus 73, which is a negative value, which indicates sign flag value is 1. And from the given options, option A is correct. Question number 5. Match the following. Left side, the names of relays are given, and the right side, their applications are mentioned. First one, Buckles relay. It is a gas operated protective relay used in oil immersed transformers. Translay relay is a differential protection scheme used mainly for feeders. Carrier current phase comparison relay is used in long transmission lines and mainly operated based on carrier communication that happens on power lines. Directional overcurrent relay is used in ring main distribution system as power flow can happen in either direction in ring main distribution system. Negative sequence relay is used in generators for protection against unbalanced currents that produce negative sequence heating in the rotor. Therefore, from the matching, option D is correct. Question number 6. A transmission line has self and mutual impedances ZS 0.8 per unit and Zm 0.2 per unit respectively. We need to find the positive, negative and zero sequence impedances. For symmetrical three-phase fully transposed transmission line, positive sequence impedance Z1 is equal to Zs minus Zm and negative sequence impedance Z2 is equal to Zs minus Zm. Since this is a fully transposed and symmetrical and balanced transmission line, Z1 is equal to Z2 and the zero sequence current Z0 is equal to Zs plus 2Zm. By substituting Zs and Zm in this formula, we get the value of positive sequence impedance Z1 as 0.8 per unit minus 0.2 per unit, which is equal to 0.6 per unit, which is also same as negative sequence impedance, and zero sequence impedance Z0 is equal to 0.8 plus 2 into 0.2, which is equal to 1.2 per unit. From the options, option D is correct. Question number 7. Grading of cables is performed in order to achieve. Grading of cables is a process used to equalize the dielectric stress across the insulation layer for achieving more uniform stress distribution. And if stress is uniform, less insulation is required for the same voltage rating, and it is not related to quality of insulation. Therefore, option A is correct. Question number 8. A three-phase transformer having a line voltage of 400 by 33 kV is connected in star delta. The current transformer on the 400 volt side have a CT ratio of 1000 by 5. We need to calculate the ratio of CT on 33 kV side. It is known that for a three-phase transformer, if it is connected in star delta, then the respective CTs are connected in delta star, which is opposite to the original connection. Considering equal three-phase powers on both sides, that is primary side power is equal to secondary side power, which is root 3 V primary IL primary is equal to root 3 into V secondary into IL secondary. From this equation, we can write IL secondary is equal to IL primary into V primary by V secondary. For the sake of simplicity, let us consider the line current flowing in primary current is equal to 1000 amps. Now, by using the above formula, the secondary side current IL is 1000 into 400 by 33 kV, which is equal to 400 by 33 amps. Now, the primary current in CT will be ICT primary. Since it is in delta connected, the current will be 5 root 3 as the ratio is 1000 to 5 as mentioned in the question. Now, let us calculate the CT ratio, which is CT ratio is equal to secondary side transformer current divided by secondary side CT current, which is equal to make ensure that secondary side CT current is also same as primary side CT current, CT ratio will be 400 by 33 divided by 5 root 3, which is equal to 7.5, which means CT ratio must convert secondary side of main transformer current, that is 400 by 33 amps into 5 root 3 amps. The CT ratio must be 7 by 5. Therefore, option A is correct. Question number 9. The input impedance Zi and the output impedance Z0 of an ideal transconductance amplifier are. Transconductance amplifier acts as voltage controlled current source, which is I0 is equal to Gm into Vi. Voltage control means it should not draw any current from the source. Therefore, Zi must be infinity. And similarly, since it is an voltage controlled current source, an ideal current source must maintain a constant current regardless of load resistance. Therefore, ideal current source has an infinite output resistance, which means Z0 is equal to infinite. Therefore, option A is correct. Question number 10. At a particular unbalanced load, the real powers specified are as follows. We need to find the balancing power. Let us draw the simple circuit which is having leaving and entering nodes. That is, we know that from KCL, entering power is equal to leaving power. Entering power is equal to 60 plus 30, which is equal to 90 megawatt, and leaving power is equal to 20 plus 25, which is equal to 45 megawatt. Since entering power is more than leaving power, the balancing power will be leaving. Therefore, balancing power is equal to entering power minus leaving power. which is equal to 90 minus 45, that is equal to 45 megawatts. Therefore, option B is correct. Question number 11. A three-phase transmission line operating at sending end voltage 400 kV and has ABCD parameters as follows. We need to find the inductive shunt reactor required for compensating Ferranti effect. To compensate Ferranti effect at no load, receiving end voltage VR must be equal to sending end voltage Vs, which means the modified generalized parameter A dash must be equal to 1. Formula for A dash with shunt reactor connected at receiving end is A dash is equal to A plus B into shunt reactor admittance. From this, A dash is equal to 1, and from the given data, A is 0.8 at an angle 0 degrees plus B is 100 at an angle 90 degrees into shunt reactor admittance. Solving this, 1 is equal to 0.8 at an angle 0 degrees can be written as 0.8, and 100 at an angle 90 degrees can be written as J into 100 multiplied with shunt reactor admittance can be written as 1 by J into shunt reactor impedance. Cancelling the common terms, solving this, 0.2 is equal to 100 by shunt reactor impedance. Finally, the shunt reactor impedance obtained is 500 ohms. Therefore, option C is correct. Question number 12. The incremental fuel cost of two generating units are given and the total load is 250 megawatts. We need to find the real powers generated by individual units, that is Pg1 and Pg2. Since total load is 250 megawatt, Pg1 plus Pg2 is equal to 250 megawatt. For optimal economic load dispatch, neglecting transmission losses, the incremental fuel cost must be equal. Therefore, IC1 is equal to IC2. Substituting the given data, IC1 is 25 plus 0.2 Pg1, which is equal to IC2, that is 32 plus 0.2 Pg2. It can be further simplified as minus 7 plus 0.2 Pg1 minus 0.2 Pg2 is equal to 0. Consider this as equation 1 and this as equation 2. Solving equation 1 and 2, from equation 1 we can write Pg2 is equal to 250 minus Pg1. Substituting this in equation 2, we get minus 7 plus 0.2 Pg1 minus 0.2. In place of Pg2, let us write 250 minus Pg1 equal to 0. Solving this step by step, minus 7 plus 0.2 Pg1 minus 50 plus 0.2 Pg1 is equal to 0. Further, 0.4 Pg1 is equal to 57. From this, Pg1 is equal to 142.5 megawatt. From equation 1, Pg2 is equal to 250 minus 142.5 megawatt, which is equal to 107.5 megawatt. Coming to options, the closely matching option is option A. Therefore, option A is correct. Question number 13. The conductors of a 1.6 km long 3-phase 3.3 kV overhead lines are in horizontal formation with spacing 762 mm between centers. The effective diameter of the conductor is 3.5 mm. We need to find the equivalent spacing. Since the overhead lines are in horizontal formation, they look like this. The spacing between adjacent lines are 762 millimeters. the distance between first and last transmission line will be sum of 762 and 762, which is equal to 1524 millimeters. For a three-phase transmission line, equivalent spacing D equivalent is given by cube root of D12, D23, D31, where D12 represents the distance between first and second conductor and D23 represents the distance between second and third conductor, and similarly D31 represents the distance between third and first conductor. From this, D12 is 762 millimeters, D23 is also 762 millimeters, but D31 is the sum of 762 and 762, which is 1524 millimeters, which is equal to cube root of 762 whole cube into 2, which is equal to 762 into cube root of 2. Solving this, we get 959.94 mm, which is approximately equal to 960 mm. Therefore, option C is correct. Question number 14. A large power system is represented by Thevenin's equivalent. The equivalent voltage and impedance are given. If a shunt capacitor bank is connected to raise the bus voltage to 1 per unit, we need to find the MVR rating of the capacitor bank. For this, let us draw a simple Thevenin's equivalent representing ETH, ZTH. From this, we need to calculate the reactive power to be supplied by the capacitor bank such that bus voltage is raised to 1 per unit. We know that reactive power QC is equal to VI sin phi, and for a purely capacitive load, sin phi is equal to 1, and from this reactive power to be supplied by capacitor QC is equal to the required bus voltage is 1 per unit, and the current flowing through the circuit I is ETH minus V by ZTH, which is equal to ETH is 0.9 at an angle 0 minus V is 1 per unit, therefore 1.0 at an angle 0. ZTH is 0.25 at an angle 90 degrees, which is equal to 0.9 minus 1 by J into 0.25, which is equal to minus 0.1 by J into 0.25, which is equal to J 0.4. From this, required MVAR rating of capacitor bank is reactive power to be supplied by capacitor bank QC multiplied with base MVA, which is equal to 0.4 into 100, which is equal to 40 MVAR. Therefore, option D is correct. Question number 15. A transmission line has equal voltages at the two ends, maintained constant by two sources. A third source is to be provided to maintain constant voltage equal to the end voltages at the midpoint of the lines, that is case 1, at 75% of the distance from the sending end, that is case 2. We need to find the maximum power transfer capabilities of the line in the original case is to case 1 is to case 2 respectively. We know that the maximum power transfer capability Pmax is equal to V square by X. For original case, Pmax is equal to V square by X. For case 1, a third source is connected at 50% of the line. Therefore, Pmax is equal to V square by X by 2, which is equal to 2 into V square by X. And for case 2, that is a third source is connected at 75% of the distance from sending end, Pmax will be V square by 3 by 4th X, which is equal to 1 by 0.75 into V square by X. Now taking the ratios of original case is to case 1 is to case 2, we get V square by X is to 2 v square by x is to 1 by 0.75 into v square by x. Cancelling the common terms, we get 1 is to 2 is to 1 by 0.75. Therefore, option B is correct. Question number 16. The geometric mean radius of a conductor in terms of the radius r of an individual strand for the three equal strands is. From the given figure, let us consider each conductor radius is r. For a three-strand conductor, geometric mean radius GMR is given by cube root of D11 into D12 into D13, where D11 is the self GMR of the strand and D12 is the distance between centers of first and second strand, and D13 is the distance between first and third strand in a conductor. Self GMR is given by R dash, which is equal to R into e power minus 0.25. D12 is the distance between centers of first and second strand, which is 2r. Similarly, D13 is also equal to 2r. Therefore, GMR of the conductor is equal to cube root of r into e power minus 0.25 into 2r into 2r. Option A is correct. Question number 17. A consumer consumes 600 kilowatt hour per day at a load factor of 0.4. If the consumer increases the load factor to 0.7 without increasing the maximum demand, we need to find the consumption of energy. For this, we need to note the relation between energy and load factor, which is energy is equal to load factor into maximum demand into time. Generally, time is considered for 24 hours. In this question, it is mentioned that the maximum demand is not changed. Therefore, Pmax is taken as constant. In the question, there are two cases. That is, case 1 is E1 is equal to 600 kilowatt hour at load factor is equal to 0.4, and case 2 is we need to find the E2 for the load factor of 0.7. From this relation, E1 by E2 is equal to LF1 by LF2, which can be further calculated as 600 by E2 is equal to 0.4 by 0.7. From this, E2 is equal to 0.7 by 0.4 into 600, which is equal to 1050 kilowatt hour. Therefore, option C is correct. Question number 18. For an SCR, during turn on and turn off respectively, the quantities responsible are. In an SCR, latching current ensures SCR remains on even after removal of gate pulse, and SCR turns off when gate current falls below the holding current. In general terms, latching current is the minimum anode current required to transition an SCR from off state to on state and maintain it even when the gate signal is removed. Holding current is the minimum anode current below which SCR turns off from its on state. Therefore, the quantities responsible for turn on and turn off of an SCR are latching current and holding current. Therefore, option C is correct. Question number 19. A particular power electronic controller develops a symmetrical output voltage from pi by 6 radian to pi radians and 7 pi by 6 radian to 2 pi radians across a resistive load over a cycle. We need to find which component is suitable for this type of application. Since the output voltage is symmetrical from pi by 6 radian to pi radians and also from 7 pi by 6 radian to 2 pi radians, it is clear that for positive half cycle, the conduction range is pi by 6 to pi radians, and during negative half cycle, the conduction range is 7 pi by 6 radian to 2 pi radians. We can say that conduction begins at pi by 6 radian, which is equal to 30 degrees. And coming to options, diode only conducts from 0 to pi radians. Two anti-parallel diodes conduct from 0 to 2 pi, but No firing angle is controlled. And coming to SR, it conducts only during positive half cycle and cannot conduct in negative half cycle. And track is the only semiconductor switch which can conduct in both direction, and track is the only semiconductor switch in the given options which can conduct in both directions and also can have a firing angle. Therefore, option C is correct. Question number 20. A single phase midpoint full wave SCR converter with maximum midpoint voltage of Vmax. We need to find the average output voltage across a raised to load for firing angle of 0 radians and pi by 2 radians. Let us quickly draw a circuit diagram of single phase midpoint full wave SCR. For single phase full wave SCR converter, the average output voltage across raised to load is given by VDC is equal to Vmax by pi into 1 plus cos alpha. At alpha equal to 0 radians, VDC is equal to Vmax by pi into 1 plus cos 0. Cos 0 is 1, therefore VDC is equal to 2 Vmax by pi. And similarly, for alpha equal to pi by 2 radians, VDC is equal to Vmax by pi 1 plus cos pi by 2. Cos pi by 2 is 0, therefore VDC is equal to Vmax by pi. From this, option A is correct. Question number 21. A 240 volts 50H single phase half wave SCR converter supplies a raised to load at a firing delay angle of pi by 3 radians. We need to find the RMS load voltage. The output load voltage waveform looks like this. We need to find the RMS value of this waveform, which can be calculated as V0 RMS is equal to 1 by 2 pi integral alpha to pi Vm sin theta square d theta into whole power 1 by 2. Let us first calculate the integral of alpha to pi sin square theta d theta, which is equal to integral alpha to pi. We can write sin square theta as 1 minus cos 2 theta by 2 into d theta, which is equal to theta by 2 minus sin 2 theta by 4 taken from limits alpha to pi, which is equal to pi by 2 minus sin 2 pi by 4 minus alpha by 2 minus sin 2 alpha by 4 . We know that sin 2 pi is equal to 0. Further simplifying, we get pi minus alpha by 2 plus sin 2 alpha by 4. Now let us calculate the V0 RMS value, which is equal to 1 by 2 pi, taking Vm square outside, Vm square integral alpha to pi sin square theta d theta whole power 1 by 2, which is equal to Vm square by 2 pi, and the value of integral alpha to pi sin square theta d theta is pi minus alpha by 2 plus sin 2 alpha by 4 whole power 1 by 2, which can be simplified as Vm by 2 into 1 by pi into pi minus alpha plus sin 2 alpha by 2 whole power 1 by 2. Substituting Vm is equal to 240 into root 2 and alpha equal to pi by 3. V0 RMS is equal to 240 root 2 by 2 into 1 by pi into pi minus pi by 3 plus sin 2 into pi by 3 by 2 whole power 1 by 2, which is equal to 240 by root 2 into 1 by pi 2 pi by 3 plus sin 2 pi by 3 by 2 whole power 1 by 2, which is equal to 240 by root 2 into 2 by 3 plus sine 2 pi by 3 is root 3 by 2. Therefore, root 3 by 4 pi whole power 1 by 2, which is equal to 240 by root 2 into square root of 2 by 3 plus root 3 by 4 pi. This is the obtained answer, but in the options, this answer is not given. Marks to all is given. Question number 22. A single phase half wave controlled SCR converter with RL load at an average load voltage of 150 volts and firing angle of 60 degrees. We need to find the supply voltage given to the converter. The circuit looks like this. The average output voltage for a single phase half wave controlled SCR converter is given by V0 average is equal to Vm by 2 pi into 1 plus cos alpha. From this we need to calculate the value of Vm. Substituting the data given in the question, V0 average 150 is equal to Vm by 2 pi into 1 plus cos 60 300 pi by 1 plus cos 60 is 0.5, which is equal to 200 pi. In general, supply voltage is always represented in terms of RMS value. Therefore, Vrms is equal to Vm by root 2, which is equal to 200 pi by root 2, which is equal to 100 root 2 pi. RMS value is not given in the answer. Therefore, marks to all is given for this question. Question number 23. A three-phase synchronous motor draws 200 amps from the line at unity power factor at rated load. Considering the same line voltage and load, we need to calculate the line current at power factor of 0.5 leading. It is given that the line voltage and load is same. Therefore, the real powers will be same, which means P1 is equal to P2, which is P1 I1 cos phi 1 is equal to V2 I2 cos phi 2. Let us consider first case as UPF and second case as 0.5 leading. In question it is mentioned that the line voltage is same, therefore V1 is equal to V2, and from the above equation we can write I1 cos phi 1 is equal to I2 cos phi 2. Substituting the data, I1 is 200 into cos phi 1, since it is at UPF, cos phi 1 is equal to 1, which is equal to I2, which we need to calculate, into cos phi 2 is 0.5 leading. From this, I2 is equal to 200 by 0.5, which is equal to 400 amps. Therefore, option D is correct. Question number 24. If the inductance and capacitance of a power system are respectively 1 Henry and 0.01 microfarad, and instantaneous value of interrupted current is 10 amps, we need to find the voltage across the circuit breaker contacts. When circuit breaker interrupts currents, also known as current chopping, the magnetic energy stored in the system's inductance is converted into electrostatic energy in the capacitance, which means half Li square is converted to half Cv square. By simplifying this equation, we get V is equal to I into root L by C. Now substituting the data given in the question, we get I is 10 amps into 1 Henry divided by 0.01 microfarad. Solving this, we get voltage across breaker is equal to 100 kilovolts. Therefore, option D is correct. Question number 25. The conducting pairs of SCRs in a bridge type 3-phase AC to DC converter with SCRs S1, S3, S5 connected in top half and S4, S6, S2 connected in bottom half of the converter, supplying a resistive load R. This is the circuit of 3-phase bridge type AC to DC converter with SCRs. In a standard 3-phase fully controlled bridge converter, thyristors are triggered in a numerical order with 60 degrees interval. Since each device conducts for 120 degrees, which means two devices, one from top half and one from bottom half, conduct simultaneously, the sequence of conducting pair is as in option A, which is also same as in option C. Therefore, for this question, option A and option C both are correct. Question number 26. For a DC to DC boost converter circuit, the order of connection of components L, C, T and MOSFET in between supply and load from left to right is. For this, let us quickly draw the DC to DC boost converter circuit. From the circuit of boost converter, we can say that option C is correct. Question number 27. In a DC to DC buck converter, when the MOSFET switch is triggered, the rate of change of current in the inductor of 400 microhenry is 7.5 into 10 power 4 ampere per second. If the converter is operated with 50 volts input, we need to calculate the output voltage of the converter. This is the buck converter circuit. We know that from the buck converter circuit, VL is equal to V in minus V out. VL is equal to L di by dt, which is equal to inductance given in the question is 400 microhenry into di by dt, which is 7.5 into 10 power 4 ampere per second. Calculating this, we get VL is equal to 30 volts. We need to calculate the output voltage of the converter, that is V out is equal to V in minus VL, which is equal to input is 50 volts minus VL is 30 volts, which is equal to 20 volts. For option B is correct. A single phase full bridge inverter with switches S1 and S2 in one leg and S3 and S4 in other leg connected along the feedback diodes D1 and D2 and D3 and D4 respectively develops a square wave voltage across an RL load. The connecting devices carrying currents during the time intervals T0 to T1, T1 to T2, T2 to T3 and T3 to T4 are. For this, let us go through the circuit diagram on the waveforms for a single phase full bridge inverter connected to an RL load, which is as shown here. Because of RL load, there is a small delay between zero crossing of voltage and currents in the output side. From this, we can say that option B is correct. Question number 29. A separately excited DC motor controlled by a single phase SCR, full control supplied 200 volts AC voltage, draws 40 amps at a firing delay angle of 45 degrees. If the armature resistance of the motor is 0.25 ohms, we need to find the back EMF. In the question it is given that single phase control rectifier is connected to a DC motor. DC motor is an RL load. Therefore, for single phase fully controlled converter connected to an RL load, average output voltage V0 average is equal to 2 Vm by pi cos alpha, and we know that Vm is equal to root 2 into V RMS, which is equal to root 2 into 200. Substituting in this formula, we get 2 into 200 root 2 divided by pi into cos 45 degrees, which is equal to 400 root 2 by pi. In cos 45 is 1 by root 2. Cancelling the common terms, we get V0 average is equal to 400 by pi volts. Now let us calculate the back EMF of the motor. Back EMF of the DC motor EB is equal to V0 minus armature voltage drop, that is IA into RA, which is equal to 400 by pi minus 40 into 0.25, which is equal to 400 by pi minus 10 volts. Therefore, option C is correct. Question number 30. In an adjustable speed DC drive operated by an AC to DC converter with armature voltage control up to base speed, we need to find the relation between torque and speed, and also the relation between power and speed. Let us see the plots of torque versus speed and power versus speed, which is as shown here. Question, it is mentioned that converter is with armature voltage control up to base speed and until base speed region. Analyzing the options, we can say that option C is correct. Question number 21. A sequence of triggering of SCRs in a three-phase bridge converter with SCRs S1, S2, S3 connected in top half and S4, S5, S6 in bottom half of the converter and supplying a R load. A similar question, that is question number 25, is also discussed. For a standard three-phase fully controlled bridge converter, thyristors are triggered in numerical order with 60 degrees interval. Since each device conducts for 120 degrees, the sequence of triggering of SCRs is as in option B. Therefore, option B is correct. Question number 32. In a linear two-port network, when 10 volts is applied to port 1, a current of 4 amps flows through port 2 when it is short-circuited. When 5 volts is applied to port 1, a current of 1.25 amps flows through a 1 ohm resistance connected across port 2. And when 3 volts is applied to port 1, We need to calculate the current through a 2 ohms resistance connected across port 2. Since the network is linear, we can represent port 2 using its Thevenin's equivalent circuit, which is as shown here. Since the network is linear, the port 2 voltage V2 is directly proportional to applied port 1 voltage V1. We can write as V2 is equal to K into V1. In case 1, V1 is equal to 10 volts. Secondary side port current I2 is equal to 4 amps. From this we can write secondary side port current I2 is equal to V2 by RTH, and we know that V2 is equal to K into V1 divided by RTH, which is equal to 4 amps. From the data, V1 is 10 volts divided by RTH is equal to 4 amps. From this, K is equal to 0.4 RTH. Let us take this as equation 1. In case 2, V1 is equal to 5 volts, RL is equal to 1 ohm, ISC is equal to 1.25 amps. Secondary side port current I2 is equal to V2 by RTH plus RL, which is equal to K into V1 is 5 volts divided by RTH is unknown plus 1 ohm is equal to 1.25 amps. Substitute K is equal to 0.4 into RTH from equation 1. We get I2 is equal to 0.4 RTH into 5 divided by RTH plus 1, which is equal to 1.25 amps. Simplifying this, 2 RTH is equal to 1.25 RTH plus 1.25. From this, RTH is equal to 1.25 divided by 0.75, which is equal to 5 by 3 ohms. And similarly, let us also calculate the value of K, which is equal to 0.4 RTH, which is equal to 0.4 into 5 by 3, which is equal to 2 by 3. Now let us calculate the value of secondary side port current I2 for case 3. In case 3, V1 is equal to 3 volts and RL is equal to 2 ohms. Let us calculate the value of secondary side port current I2 is equal to V2 by RTH plus RL, which is equal to V2 is equal to K into V1 divided by RTH plus RL, which is equal to, from the previous, K is equal to 2 by 3 and V1 is 3 volts divided by RTH is 5 by 3 plus RL is 2 ohms. Solving this, we get I2 is equal to 6 by 11, which is equal to 0.545 amps. Therefore, option C is correct. Question number 33. What will be the shape of the current in the circuit? Here, input voltage V of t is equal to VDC plus Vm sin omega t. Since the load is purely inductive, I of t is equal to 1 by L integral V of t dt, which is equal to 1 by L integral VDC plus Vm sin omega t dt, which is equal to VDC by L into t plus Vm by omega L into cos omega t plus some constant k. By observing this, from this equation, we can say that the current in the circuit has two terms and Vm by omega L into cos omega t. This is a sinusoidal function. We need to select the option which has both ramp and sinusoidal waveforms, which is option D. Therefore, option D is correct. Question number 34. In a steady state, what will be the capacitor C2 voltage if C1 is equal to C2? In steady state, since input is DC, capacitor acts as open circuit. C1 becomes open circuit. No continuous current can flow from DC voltage source through the circuit. Therefore, I is equal to 0. Since the current from input is 0, the current flowing through the resistor is also 0. From Ohm's law, we can say that voltage across resistor VR is equal to IR into R. Since IR is equal to 0, voltage across resistor VR is also equal to 0. The capacitor C2 voltage will be equal to resistor voltage as they are in parallel. Therefore, we can say that capacitor C2 voltage is equal to 0. Option C is correct. Question number 35. What will be the rise in the capacitor voltage per second? We know that current through the capacitor I of t is equal to C dV by dt. From this, dV by dt is equal to I of t by C, which is equal to current flowing in the circuit is 2 amps divided by capacitance is 2 microfarad, which is equal to 1 into 10 power 6 volts per second. This answer is not given in the option, therefore marks to all is provided. Question number 36. What will be the average power drawn from the voltage source? We know that average power is equal to product of voltage into current, that is V of t into I of t. Average power drawn from voltage source V of t is Vm sin omega t. Substituting in the power formula, P is equal to 1 by t integral 0 to t Vm sin omega t into I. Since Vm and I here are constant, we can take it out of the integral. Therefore, average power P is equal to 1 by t Vm into I into integral 0 to t sin omega t dt. The integral of sin omega t is 0. Therefore, we can say that P average value drawn from the voltage source is 0. Therefore, option B is correct.
Question number 37. In the given circuit, if R1 is equal to R2, what should be the voltage magnitude to have 0 current through R3? For current to be 0 through R3, voltage at this node must be equal to 0. Applying KCL at this node, considering currents leaving through this node, the equation obtained is 0 minus 5 by R1 plus 0 minus V by R2 must be equal to 0. Since R1 is equal to R2, minus 5 minus V is equal to 0. Therefore, V is equal to minus 5 volts. Therefore, option D is correct. Question number 38. A series RL circuit is excited at t equal to 0. By closing a switch, we need to calculate the value of d square I by dt square at t is equal to 0 plus, assuming 0 initial conditions. Let us apply KVL to this circuit. From KVL, we can write V is equal to R into I of t plus L into di of t by dt. From this, di by dt can be written as V minus R into I of t by L. Applying 0 initial conditions, as current through the inductor at t is equal to 0 is 0, the current in the inductor at t is equal to 0 plus will also be equal to 0, as inductor never allows sudden changes in current. Therefore, we can write di by dt at t is equal to 0 plus is equal to V by L. Let us consider this as equation 1. Differentiating equation 1, we get 0 is equal to R into di of t by dt plus L into d square I of t by dt square. Now, from this equation, d square I of t by dt square can be written as minus R by L d into di by dt, which is equal to minus R by L into, we already know that di by dt is equal to V by L. Substituting here, we get d square I by dt square is equal to minus Rv by L square. Therefore, option D is correct. Question number 39. Determine the current through the capacitor during steady state. In steady state, inductors act as short circuit and capacitors act as open circuit. Therefore, we can say that current through the capacitor is 0 amps. Option B is correct. Question number 40. If the voltage across the resistor is equal to the supply voltage, what will be the ratio of voltages between L and C? Let us consider supply voltage as Vs, voltage across inductor as VL, and the voltage across capacitor Vg, and similarly voltage across resistor as Vr. For a given series RLC circuit, supply voltage can be written as square root of Vr square plus VL minus Vc whole square. In the question, it is mentioned that voltage across resistor is equal to supply voltage. Therefore, Vs is equal to Vr is equal to, let us take it as V. Substituting in the above equation, we get V square is equal to V square plus VL minus Vc whole square. Cancelling this, we get VL is equal to Vc. This condition represents electrical resonance, and from this, the ratio of voltages between L and C, that is VL by Vc, is equal to 1. Therefore, option A is correct. Question number 41. In the circuit given below, we need to calculate the current through the capacitor at t is equal to 0 plus and also at t is equal to infinity. At t is equal to 0 minus, the source is inactive. In the circuit, it is mentioned that supply voltage is equal to 2 into e power minus t into u of t, which means at t is equal to 0 minus, the source is inactive. Therefore, voltage across capacitor Vc of 0 minus will be also equal to 0, and at t is equal to 0 plus, from initial conditions, since the capacitor does not allow sudden changes in voltage, voltage across capacitor at t is equal to 0 plus will also be equal to 0, that is Vc of 0 plus will be equal to 0. Now from KVL, Vs is equal to Vr plus Vc, and from this equation we can write Vs of 0 plus is equal to voltage across resistor Vr is equal to I into R, that is R into I of 0 plus Vc of 0 plus. From this, I of 0 plus can be written as Vs of 0 plus minus Vc of 0 plus divided by R. From this, I of 0 plus is equal to Vs of 0 plus is 2 minus Vc of 0 plus is 0 divided by R is 1 ohm, which is equal to 2 amps. Now, as t tends to infinity, Vs is equal to 2 into e power minus 0, which is equal to 0 volts. Since input voltage is equal to 0 at t is equal to infinity, steady state current at t is equal to infinity will also be equal to 0. Therefore, I of infinity is equal to 0 amps. From this, option D is correct. Question number 42. A single phase transformer has turns ratio of 1:2 and is connected to a purely resistive load. The magnetizing current as well as the load current drawn is 1 amp. Neglecting core losses and leakage reactances, we need to calculate the primary current. Secondary load current reflected to primary is I2 dash is equal to I2 into N2 by N1, which is equal to I2 is 1 amp into turns ratio N2 by N1 is equal to 2 by 1. From this, I2 dash is 2 amps. Magnetizing current Im is equal to 1 amp from the given data, which lags the primary voltage by 90 degrees. Now, total current flowing in primary will be I1 is equal to square root of I2 dash square plus Im square, which is equal to square root of 2 square plus 1 square, which is equal to root 5, that is 2.236 amps, which is I1 is approximately equal to 2.24 amps. Therefore, option C is correct. Question number 43. A single phase 100 kVA 1000 by 100 volts 50 Hz transformer has a voltage drop of 5% across its series impedance at full load. Of this, 3% is due to resistance. We need to calculate the percentage regulation of the transformer at 0.8 lagging power factor. We know that voltage regulation is equal to percentage R into cos phi plus percentage impedance into sin phi. Percentage R is given in the question. We need to calculate the percentage x value. Percentage x is given by square root of percentage z square minus percentage R square, which is equal to square root of 5 square minus 3 square. Therefore, percentage x is equal to 4%. We need to calculate the percentage regulation of transformer at 0.8 lagging power factor, which means cos phi is equal to 0.8, and if cos phi is equal to 0.8, sin phi is equal to 0.6. Substituting the values in the equation, we get percentage voltage regulation is equal to 3 into 0.8 plus 4 into 0.6, which is equal to 4.8%. Option A is correct. Question number 44. Which of the following statements is valid for the transformers? There are few statements mentioned in the options from open circuit test and short circuit test. Open circuit test measures core losses, not the copper losses, and in open circuit test, transformer draws only no load current, which is highly inductive due to magnetizing component, that is, at no load, power factor is very low. And similarly, during short circuit test, current is at rated load conditions and power factor is non-zero. From this, going through options, we can say that option D is correct. Question number 45. A single phase transformer has no load loss of 64 watts as obtained from the open circuit test. When a short circuit test is performed with 90% of the rated current flowing in its both LV and HV windings, the measured loss is 81 watts. The transformer should exhibit maximum efficiency at. We need to calculate the maximum efficiency that the transformer can exhibit. As discussed in the previous question, from open circuit test, we will get core losses. Core losses given in the question is 64 watts and copper losses mentioned in the question is 81 watts at 90% rated load current. Copper losses at full load is equal to 81 watts divided by 0.9 whole square, which is equal to 100 watts. And it is known that maximum efficiency occurs at core losses is equal to x square into copper losses. X is equal to square root of core losses divided by copper losses, which is equal to square root of 64 divided by 100, which is equal to 0.8, that is 80% of the load. Therefore, option C, 80% of the rated current is correct. Question number 46. The value of Z in the given figure is most appropriate to cause parallel resonance at 500 Hz is. We know that resonant frequency omega is equal to 2 pi f, which is equal to 1 by root LC. To cause electrical resonance, there must be two components, that is inductor and capacitor. Since the inductor is given in the question, we need to calculate the value of capacitor, and from this equation we can write LC is equal to 1 by 2 pi f square, and from this capacitor value C is equal to 1 by L into 2 pi f square. Substituting the parameter values in this equation, we get C is equal to 1 by L is 2 Henry into 2 pi, frequency given in 500 Hz square. Solving this, we get capacitor value C is equal to 0.0506 microfarad. Therefore, option D is correct. Question number 47. A 3-phase 4-wire 400 volt system is supplying a balanced star connected load with some impedance and voltages to neutral are given, that is phase voltages are given. We need to calculate the current in the neutral wire. In a perfectly balanced 3-phase 4-wire system connected a balanced load, the current in the neutral wire is the phasor sum of three symmetrical equal magnitude currents displaced by 120 degrees. In the question, if we observe, the voltages to neutral are displaced by 120 degrees. Therefore, the current in the neutral wire is equal to 0. Option B is correct. Question number 48. An 8-pole DC generator has simplex wave-wound armature containing 32 coils of 6 tons each. Its flux per pole is 0.06 Weber and the machine is running at 250 RPM. We need to calculate the induced armature voltage. We know that induced voltage is equal to 5Zn by 60 into P by A. In the question, the value of phi is given, n is given, and number of poles is also given, and for simplex wave, A is equal to 2. Let us calculate the value of Z, which is equal to number of conductors which is equal to 32 coils into 6 turns per coil into 2 conductors per turn. Calculating this, we get the value of Z as 384. Now substituting the data in the equation, we get Eg is equal to 0.06 into 384 into 250 RPM divided by 60 into number of poles is 8, and for simplex wave A is equal to 2, and solving for this we get the value of induced armature voltage as 384 volts. Therefore, option C is correct. Question number 49. A 3-phase balanced load which has power factor of 0.707 is connected to a balanced supply. The power consumed by the load is 5 kilowatt. The power is measured by 2 wattmeter method. We need to find the readings of 2 wattmeters. It is given that total load is 5 kilowatt. Therefore, W1 plus W2, which are readings of wattmeter 1 and wattmeter 2, must be equal to 5 kilowatt. And we also know that tan phi is equal to root 3 into W1 minus W2 divided by W1 plus W2. And to calculate the value of phi, in the question it is given that cos phi, that is power factor, is equal to 0.707. From this, tan phi is equal to cos inverse of 0.7, which is equal to tan 45 degrees, which is equal to 1. Therefore, tan 45, which is equal to 1, is equal to root 3 into W1 minus W2 divided by 5 kilowatt. Consider this as equation 1 and this as equation 2. Now solving equation 1 and 2, we get W1 is equal to 3.943 kilowatt and W2 is equal to 1.057 kilowatt, which is approximately W1 is equal to 3.94 kilowatt and approximately W2 is equal to 1.06 kilowatt. Therefore, option A is correct. Question number 50. The torque versus speed curve of an induction motor is given and 4 points are marked W, X, Y and Z. Which one of them represents the operation at a slip greater than 1? We know that slip S is equal to Ns minus Nr by Ns. When motor runs in opposite direction to rotating magnetic field, Nr will be negative and therefore slip will be positive. From the torque versus speed curve, we need to choose the point where speed is negative, that corresponds to slip greater than 1. In the given figure, point W lies in the negative speed region. Therefore, option A is correct.